to the club. All right, so find the slope of the tangent line to the graph of y equals x squared at the point 3,9. All right, so we'll come back to that really kooky one, the next example. By the way, if you're in the market for typo bonus, you may notice little things like, for example, this one has an underline, this example has an underline, but this one doesn't. All right, so, and you might take a look and see, actually, a lot of them have underlines and a lot of them don't. So a typo would be something like, be consistent with whether you're going to underline example or not underline example. All right. So anyway, looking at y equals x squared. Now, if we're going to tackle this one, we go back to our difference quotient derivation. I'll just show you real quick. We have this variation of, oh, well, actually, no, this isn't even the derivation. That's just like breaking it down to brass tacks here. But if we go to this variation of the difference quotient, which is f of a plus h minus f of a all over h, this guy, then we can actually jump right to the slope without getting the function that gives the slope to begin with. So I'm going to snag this one. I'm just going to show you because it's kind of nifty, but it's not always necessary. So it gets glossed over fairly frequently, and I didn't want to do that. All right. So the difference here is that normally it would be f of x plus h minus f of x all over h. But since we are given a point, it's a solid point, we have the choice. We can find the derivative in terms of x and then replace it later on with whatever the a value is, or we could leave it in terms of a straight away and go from there. All right. So if I tell you that this point is a comma f of a, then what we're really saying is a is equal to 3. All right. So what I could do is I can modify my difference quotient. Instead of saying f of a plus h minus f of a all over h, I could say f of 3 plus h minus f of 3 all over h. It's a deviation from the process. It's basically a slight deviation, but it's basically saying, all right, instead of working with it in terms of x, only to substitute out an x later on and replace it all with a 3, why not plug in the 3 straight away? Right? There's pros and cons either way, but you could still kind of play it out and see where it takes you. Right? So the original function y equals x squared, we could say that that's f of x is equal to x squared, in which case f of 3 plus h would be 3 plus h squared. All right, all we're doing is replacing the x with the 3 plus h. So this expansion would be 3 plus h squared minus, well, f of 3 would be whatever you would get when you plug in a 3 for x, so minus 3 squared all over h. We could expand this out using the FOIL method for the 3 plus h squared. This is the same as saying 3 plus h times 3 plus h minus, well, this is clearly a 9, over h, distributed further, or I'll distribute a period, 9 plus 6h plus h squared minus 9 over h. All right, so just foiling it out, but then we would cancel the 9 with the negative 9, ending up with 6h plus h squared over h, which in turn, when you distribute or factor, out the h on the top, 6 plus h over h, would give you 6 plus h. And then if you just need the slope of the tangent line, I put the emphasis on the wrong syllable there. It's not really the syllable, it's more like the word. But I emphasize the wrong thing, is what I'm getting at. If you're looking for the slope of the tangent line, as opposed to the slope of the secant line, because this is the slope of the secant. If you want the slope of the tangent, you would say the limit as h approached 0 of 6 plus h, and that would give you a result of 6, which in turn would be the slope of the tangent. All right. So if you were to carry out this process using x's instead of 3's, you would have had an x here, an x here, and an x squared here. You would have distributed all of this out, cleaned it up, and then later on substituted in a 3. It really is 6 of one, half a dozen of the other. It's the same thing, right? It's just this kind of gets the x out of the way pretty quickly. But it's entirely up to you. Now, what I will say is on a test, any kind of assessment, if I ask you to find the slope at a point, I'm really just looking for the number anyway. So it will never be a question where it says find the slope at a particular point where it asks you to do it in a particular way. That you'd have the option to do it any way you want. Even if it asks you to show work, that work could be a Desmos calculator. So it really is up to you. All right, so this is just another strategy. That's why this one was so further down the line. And actually, after the fact, I realized I was using A's here instead of C, like the definition says. Apologies for that. That's not really a typo. It's just when I make notes, or when I type up notes, I have an idea in my head of what I want to get or what I want to type. And so I go to the internet looking to see if anybody typed the thing that I was looking to type. Most of the time people get pretty close. So I copy, paste, edit, and so on, and then sometimes forget to change things. Long story short, we're calling this another typo. These should both be A's. All right, in both cases. So, like I said, if you're in the market for typo bonus, remember you can get up to 3 bonus points per unit for just sending me a message saying, I found a typo on this page. This is what the typo is. And this is, if it's not obvious, you just tell me what to do to fix it. As long as you're the first one to submit it, you get the bonus credit. All right. So just keep submitting. My notes get better. You all get bonus. We're all happy. All right. So just keep that in mind. If I point it out in class, you're duking it out with everybody else, but it might get you thinking, like, especially that underline thing, for example, maybe you don't get it for page 16, but maybe you get it on page 60, you know? So just keep your eyes open for stuff like that. All right. The next example, we started it off last class. Find the slope of the tangent line to the graph y equals the cube root of x, okay, at x equals 0. So in theory, we could use this same approach, but what we're going to actually do here is pretty algebra intensive. So we want to make sure that we get the skill down. So I don't want to confuse things too much. Okay, so I started this off with f of x is equal to cube root of x. That was given. Then f of x plus h swaps out the given x for an x plus h. All right, so that part was fine. We plug it into the difference quotient, which again is f of x plus h minus f of x all over h. That's the ordinary difference quotient, not the alternate. We'll talk about the alternate in a couple of minutes. I'll show you how that works for this problem as well. All right. We got to this point, and that's where I left you in suspense for 2 days. If you worked it out yourself, great. If you looked it up because you couldn't handle the suspense, that's fine too. But what we're going to do here is figure out how we can algebraically modify this, because when we go to take a limit, ultimately it's going to be the limit as h approaches 0. All right. If h approaches 0, for this ratio in its current form, we're going to get something that's undefined. Well, actually, it'll be indeterminate, which is kind of worse, because what that means is that you can't call it a day. If it's undefined, it could just be that there's no solution. It could just be that it's infinity or something like that. You know, limit does not exist. Okay. But in this case, it's more like, no, there's an answer, and you got to do the algebra to get to that answer. All right. So the algebra that applies here is actually a rule from a few semesters ago, an algebraic rule. It's the difference of two cubes. Right. So the rule, difference of two cubes, a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. It's one of those rules where you know you've seen it before, but you also know that you use it so infrequently that it's almost designed for you to forget it. I'm just making that 3 look a little nicer. All right, so that's the rule that we're going to apply here. And you may look at it and say, how on earth are we going to apply that rule? That doesn't, yeah, there's no way that's going to happen. Just wait. It might be somewhat shocking to see how it actually develops. It's kind of cool. Right. So what we're going to do is we're actually going to manufacture this rule as part of the solution. We already have part of it. We need the whole thing. Right. So if you remember conjugates, like multiplying by a conjugate when it comes to radicals, then you're kind of on the right track. Except when you're dealing with cubes, it's a little bit more complicated. Right. So let me show you what would happen if I had an expression here instead of a cubed plus b, minus b cubed, I had x plus h cubed minus x cubed. Okay, which is kind of like what you see here, except it's cubed instead of cube rooted. All right, so I'm going to show you that, and then I'll show you what's really going to do it for us. Okay, if I had something like this, what we would get as a result would be, because if you look at the relationship, power of 3 becomes power of 1. So this would become x plus h, and this would become an x. All right, and that's nice. It's great, but it's not quite what we need. All right, but it's a step in the right direction. I'll carry out the rest of the process just so you see, because I never like it to be the case where it's like, well, just do this. Why? Because isn't it obvious? Well, no, it's not obvious. That's why we didn't do it together to begin with. All right. So the a squared is, you're taking this term, whatever this term is, and raising it to the second power. So that would happen with this term. So x plus h squared, then plus ab. So whatever your ab terms are, so that's these two. So that would be x times x plus h. And then the b squared, I'm just taking whatever the quantity b is. Because again, b could be an entire function. I mean, it's just a placeholder, the b. So plus, that would be x squared, right? So that's one possibility you might consider. You could simplify, you try to clean it up. But if you were given an expression, one expression cubed minus another expression cubed, there would be a whole expansion related to that, right? But what I actually need here is to end up with a cube root. So if I started with x plus h here, just an x plus h. So x plus h to the first power minus an x to the first power. Since the first entry in the binomial is going to be the cube root of the first entry in your original expression, cube root, is what happens when you divide the exponent by 3. I would get x plus h to the 1/3 power. Right? I'd also get, for this one, an x to the 1/3 power. And then using the same relationship where I square this one, x plus h would become, or it would be raised to the 2/3 power. Then I would have, this is going to be ugly, but x to the 1/3, x plus h to the 1/3. I missed the minus along the way. And then finally, x plus h, x to the 2/3 power. All right. So I mean, it gets pretty messy, but I always remember this rule by saying cube root, square, multiply, square. It only helps if it's kind of fresh in your mind. But when you start off with, and I'm going to kind of clean this up a little bit, just so I can really kind of emphasize. I'm going to get rid of all the highlighting, get rid of all this stuff, the extra fluff here. Oh, too much, got rid of too much. Yeah, that might be good enough to get rid of. All right, so we have 2 terms that we're starting with. And this is how I always remembered it. If it helps you, that's great. If not, every assessment is pretty much open notes. So make sure you have this written down somewhere. All right, so, and let me clean this up. That was going to bother me, so I'm just taking care of it. So my first entry in my expansion, it's not really an expansion, but it looks bigger, so I just call it that. This is the cube root of the a cubed, right? So cube root. The b is the cube root of b cubed. And what we do is we square this, then we multiply these two, and then we square this. So I say cube root, square, multiply, square. Then the only thing that becomes an issue is, well, how do you get the sign distribution? The minus, the plus, the plus. There's a little acronym I heard, well, a student told me that they read it in a textbook at some point, and I liked it, so I kept it. It's SOAP, which stands for same, opposite, always positive. It was kind of cool, so I kept it. So these are for the signs. All right, so you would keep the first sign the way it was originally. The second one would be the opposite of the original, and the last one's always positive. Thought it was pretty cool, so I just went with it, Sometimes that happens. So then you look at this and say, okay, that's cool. Thanks for the walk down memory lane, dude. Really appreciate it. Can you get on with the show here? Well, that kind of was the show, because I'm going to take my slope of the secant here. Actually, I'm going to even rewrite it. I'm just going to bring it over. We had the cube root of x plus h is really the same as saying x plus h to the 1/3. The cube root of x is the same as saying x to the 1/3. We still have that h there. What we're going to do, I'm going to bring this back in. What we're going to do is we're going to multiply the top and bottom by this. All right, so we're going to multiply the top and bottom of the fraction by that nasty expression. But it's actually going to work out really nicely. It's just, you got to believe, So we know that if I multiply this by this, the result ought to be this. So that's what we're going to force to happen. we're going to multiply these two expressions, this one and this one, and the result is going to be x plus h to the first power. If you want to write that, by all means, go for it, minus x. Right? Because that's how the rule expanded out. On the bottom, we're up the creek. There's really nothing we can do. We could write these two things together adjacent to one another, and that's about it. But it's really all about the numerator anyway. If I simplify the numerator, I'm going to be able to cancel the x with the negative x. That's going to leave me with just an h up top. So rewriting, and really honestly, that's probably going to be the biggest bugaboo with all this, just rewriting and rewriting and rewriting. I'm going to have h over h times that big mess. The h's would then cancel to a 1, and now the troublemaker is gone. The troublemaker was the h in the bottom of the fraction. Yeah, it's definitely an intense one. And it's only gonna feel worse when we get into the shortcuts, because it's like, oh, all that, and we could have done it this way. Part of it has to do with appreciation of the shortcuts, but another part of it has to do with the fact that you will eventually come across what are known as multivariable functions if you get that far. If you're going the full calculus route, you know, Calc 2, Calc 3 and all that, where it will pay dividends for you to know how to simplify this stuff out algebraically. Honestly, if this is one of those skills, this and the unit circle, where if you have those ideas, like some good, solid, fundamental algebra skills and the unit circle, then that's going to get you a long way in your calculus life. Right. So,
Professor, I have a question. Sorry.
Sure.
So on the second line, after the x plus h cubed minus x cubed equals all that, could you explain to me again why you how did all that become like x plus h prime and then equals to like x plus h 1/3 minus x 1/3?
So it didn't become that. Just think of this as trial 1 and trial 2. So it was like, all right, I need to somehow figure out how to simplify that. So let me try expanding x plus h cubed minus x plus h. X plus h cubed minus x cubed. And then I said, okay, well, that didn't work. That didn't get me what I needed. So it's kind of like, all right, no good there. So let's try something else. So what we did was x plus h to the first power minus x to the first power to see what that expansion would be. So it wasn't that this led to this. It was that this first trial was more like a false start, just to show you how the rule worked. But this is the one that we wanted.
But Professor,
Okay, thank you.
how did you know that that's the one that you wanted?
Because that's the one that had the x plus h to the 1/3 power in it.
Mm-hmm.
So x plus h to the 1/3 minus x to the 1/3. And so since our slope of the secant had an x plus h to the 1/3 minus an x to the 1/3, once I realized that that's the missing ingredient, that's the piece that we were looking for, that all I would have to do is multiply my numerator from the secant by this whole expression here, and we would end up with this one. That was the recipe for getting the process taken care of.
Okay, thank you.
Yeah, no problem. Right, so now we have a slope of secant. It's hideous, but it's going to work, because we're going to find the limit as h approaches 0. We're going to replace every one of these h's with a 0. because it's not going to make it undefined or indeterminate. So, oh, I'm going to change my size again. Each one of these h's get replaced with a 0. And so we would be looking at now 1 over x to the 2/3 plus x to the 1/3 times another x to the 1/3 plus x to the 2/3, which when you look at the middle one there, that's really just, keep the base at the exponents. That's another x to the 2/3. Okay, so this here amounts to x to the 2/3. So I have 3 of those x to the 2/3. So 1 over 3x to the 2/3 would be my derivative. All right, so this is the derivative. So we would then say f prime of x is equal to 1 over 3x to the 2/3. And now if I want to find, it's asking for just the slope, not the equation, f prime of 0. After all that, in heartbreaking fashion, we end up with 1 over 3 times 0 to the 2/3, which is 1 over 0. And now it's like, what does this mean? Does it mean there's no solution? Or what does it mean, something even more diabolical? All right. Well, undefined could mean a bunch of different things. It could mean that the limit does not exist. It could mean that there's no solution to a problem. It could also mean, in the context of slope, because remember, this is the slope of the tangent line. Slope of the line tangent to the curve at any point along the curve, but in this instance, it's the slope of the line tangent to the curve at the x value of 0. So a slope that's undefined often means vertical. Is this a vertical tangent? All right. Now, if you really test this out analytically, you'll be able to make the determination using limits. It's not the highlight of everybody's day. Let me just put it that way. So what we tend to do is just take a look at the picture and say f of x is equal to the cube root, but I'm just going to use x to the 1/3. And then just essentially see what's happening around 0. If I zoom in a lot, it does look like it's going vertical. All right. And so what's happening here is I could take that question mark away. In this context, that undefined is talking about a vertical tangent. All right. So if you want to test this out analytically, so I'll show you that in a sec. And I'll also show you another way to do the problem. So we're only just getting started with this one. All right. So if you want to test this out using limits to verify that you're talking about a vertical tangent, what you would have to do, and I'm just going to move this up. You know what? Honestly, I think I'm just safer including another page. So let me do that. So to verify a vertical tangent. Oh, also in terms of typos, I also accept not enough room on the page. Like, I don't know how many people are actually using the handout. Like if you printed it out or if you're doing digital ink or anything, I would imagine lots of people are just doing it in a notebook. But if you see me getting to a point where I have to go to a different page in order to finish a problem, that means that there wasn't enough space on the page. All right. So you could say not enough space for the example, the second example. No, this would be the third example on page 16. Oh, by the way, just notice something at the top. Yeah. So my example naming is a little iffy. EX, for example, and I numbered it. This is number 7, and then I go right back to example without an underline, then example with an underline. So yeah, there's a lot of typos for everybody here. I mean, you probably all get your typos. If you just look through the notes, you probably find three unique ones without even having to try. Okay? I make those kind of mistakes all the time. It's just kind of like haphazard. So anyway, to verify a vertical tangent, what we do is first, why am I writing first? I don't know. Sometimes I get in my own head. So the first thing you're going to do is find the derivative at the point. So whatever it is, f prime of a, that should be equal to undefined. All right, f of a, so the original function must exist at that point. All right, meaning it's not a discontinuity. All right, so that's showing that there are points coming in and going out of that location. But most importantly, there's a point at that location. That's what we care about. All right, so that's the second thing that we look for. Because most of the time you got to figure out the derivative anyway. So it's sort of, these two can kind of be interchangeable, but most of the time you got to do this no matter what. All right. So the third thing that you're going to do is find the limit as x approaches a from the left of the derivative function. And then the limit as x approaches a from the right of the derivative function. So not the original function. All right. So not the original function, it has to be the derivative function. That's why I'm saying number 1 is probably going to happen no matter what, because in order to do this, you need to know what the derivative is one way or the other. All right. So you got to compute those two things. Now, what's going to happen is these two results are going to go to the same infinity. All right, they have to go to the same infinity, meaning if one goes to positive infinity, all right, the other also has to go to positive infinity. If one goes to negative infinity, the other also has to go to negative infinity. If that's the case, then you've verified a vertical tangent. All right. So I would then, I've already verified, the first two things, that my first derivative is undefined at that location. It exists. I mean, visual inspection. I mean, I'm looking at a solid point right here. All right. So verified. So, but if you need to really state it, you could say f of 0 is equal to 0 and just be safe about it. But what we would then need to do is find the limit as x approaches 0 from the left of f prime of x, and the limit as x approaches 0 from the right of f prime of x, and see what you get. All right. And so here, what we're going to do, or what we would have to do, is you'd have to evaluate this numerically. All right. So in this case, this is the same as saying the limit as x approaches 0 from the left of 1/3 times x to the 2/3. And then it would really be the same thing. Oops. I want the equal sign too, but with a plus sign after the 0. And you will end up using a calculator to support your work. But the idea is that you should be able to come up with some kind of infinity. All right. So, and if you want to, sneak a look at the calculator to get an idea of what's going on, that's fine too. The benefit of the Desmos calculator is that it'll graph the the derivative function for you. Won't tell you what the derivative function is. You're on your own for that, but it'll graph it for you. So you type in f prime of x. Oh, I need the of. I need the of for crying out loud. Fat fingers. It's like I was going for the open paren and I kept hitting the x. All right. So I type it in. It says in Desmos that I should be looking for a blue graph. I don't see a blue graph, so let me bring it out a little bit. Oh, there's a blue graph. All right. So I would ignore the red and say, all right, if I'm coming in from the left, where am I going? Looks like I'm going up forever. All right. If I'm coming into 0 from the left, looks like I'm going up forever. If I'm coming into 0 from the right, it looks like I'm going up forever. All right. As I approach 0 from the right, I'm getting bigger and bigger and bigger. If you're not sure, just zoom out like a lot and then zoom back in and just verify that you have two distinct curves that are both going in the same direction. All right. You really got to zoom the living daylights out of it in order to see, but you get there. All right. So you see we have two curves that are, and again, it doesn't matter which infinity they're going to. It's just that they have to go to the same infinity. All right. It turns out that they're both going to infinity, to positive infinity. And so we have checked for this. And so that's the analytic verification of a vertical tangent. So therefore, f of x has a vertical tangent at x equals 0. Right. So, you know, there's a lot more going on there than you would necessarily think going into the problem. But, and especially since, I mean, you probably remember this from pre-calc when, especially if you had to do a lot of, if you had a very algebra-minded teacher that wanted you to do everything out by hand, and maybe you're an algebra-minded person where you just like to do everything by hand, and you had to find things like, you know, x-intercepts and all that good stuff. You were using a lot of synthetic division and all that good stuff. And then, you know, like you have the other person that's coming along being like, yeah, that's all good, but I know the x-intercept is 0 because that's what it says right here. So I find it awesome that you're able to do all that by hand. However, if I just need an answer, can I just look at the graph? You know, and the answer is, of course, but you got to be prepared to go both ways, as you know, right? So it's just my style allows for the flexibility of kind of choosing your own adventure.
So
To some extent, or for most extent.
Defined is why is it undefined? Like initially.
Why is the condition undefined? Because in order to be vertical, you know, if you think about just an ordinary slope from like algebra 1, you had a positive slope, you had a negative slope, you had the 0 slope, and then you had the no slope. No slope is the case where the fraction when you did change y over change in x was undefined. Right. So in order to have a tangent line that's vertical, the first condition that needs to be met is that its slope has to meet the condition of being that of a vertical line, which is undefined. Right. So 0, like 0 over 1 for a horizontal line, but 1 over 0 for a vertical line.
Oh, so because the denominator is 0 in the slope.
Right. Exactamundo.
Okay.
All right. And so then when we get into tests for differentiability, we're looking for certain things to be in play. There's the classic definition. If a function is continuous, I'm sorry, if it's, geez, I almost said it backwards. If a function is not continuous at a point, then it's not differentiable at that point. So that's a good first sort of step in determining differentiability. All right, differentiability, and I mentioned this last time, it's another way of saying it is being derivativable, right? As in, can you find the derivative of it? Yes, in terms of x, but does that derivative have a meaning or have any kind of reasonable meaning at the point that you're looking at, right? So you could have a function that's perfectly well derivativable or differentiable for many, many points. In fact, maybe all but 1 point, negative infinity to infinity, except for maybe 0, right? If there's ever an instance where there's a discontinuity, then you're dealing with something it's not going to be differentiable wherever the discontinuity is. And I think that would make sense, because how are you going to find the slope of a curve at a location where the curve doesn't exist? All right. So those are usually the easy ones to find. But the other possibilities are, and when you think about it from the reverse, like just because a function is continuous doesn't mean it's differentiable. Your exceptions are the cusp and the corner. All right. So if you ever see any graph that comes to a point, then it's not going to be differentiable at the point, right? Whatever the x value is of the point, it won't be differentiable at that location. It'll be continuous, but it won't be differentiable. All right. So let me just show you what a cusp looks like. A cusp, well, the corner is the easy one because it kind of looks the way it sounds. There are other variations of this, but here's an example of a corner. The cusp is an instance where it bows in to a point. This would be an example of a cusp. Typically, a cusp will occur for a single function. A corner usually occurs when you're dealing with multiple functions. Right, that are pieced together. Now that's typical, right? There are exceptions to everything. All right, so these are the typical cases, because I mean, this looks like an absolute value function, but you say absolute, I say piecewise function with 2 linear functions. You know what I'm saying? So it's you know, you say tomato, you know, that kind of thing. All right, so another example of a corner could be something like this. Doesn't really look much like a corner, all right? But this would be the location of the corner, all right? All because you're piecing together 2 different functions. This is probably some sort of trig function, maybe like a high degree polynomial function, and this would be a linear put together, all right? Now, when you're testing to determine if you're dealing with a cusp or a corner, it's actually pretty easy, all right? Well, okay, let me be fair about it. It's easy once you found the first derivative. So let me actually just schmidge this over, talk about the cusp for a minute. And actually, let me make sure I didn't type any of this stuff. Yeah, I definitely didn't type any of this in this note packet. Yeah, that's the drawback of teaching 3 different variations of the same course, that I know I have a better version of this notes. I just don't know where it is, or these notes, sorry. So the cusp, the test would be that f of a exists and the limit as x approaches a from the left of f prime of x and the limit as x approaches a from the right of f prime of x are equal to opposite infinities. All right, so it has a lot of the same ingredients as the test for a vertical tangent. One thing that you don't have to worry about is whether or not the first derivative exists, because you can assess that visually. Although it will also be the case where it does, the first derivative is undefined as well, because it does go vertical at the cusp. So you could also look for that. However, just like in the case, I kind of like, I feel like you probably don't need to bother with that, because you look at the picture, like in this case, you're like, well, it's vertical here, so it's probably a vertical tangent. Let me just jump right to the meat of the test. But I guess I could chuck it in there also. F prime of A is undefined. All right. So for a corner, the test is actually a little bit simpler. We don't really worry about infinities there. I mean, it's possible that it could happen, but it's actually less complicated. The only thing that's complicated here is me actually physically writing it, right? Your function needs to exist at the point. I got to resize. Your function needs to exist at the location, whatever the A value is, and your limit of the first derivative coming in from the left and coming in from the right, they could be whatever as long as they don't equal each other. They just got to be different. And that's a justification for a corner. Aside from, you know, the obvious thing of like, I looked at the picture and I see a corner. All right. It's kind of like in that pre-calc example is like, how did you know that there was an x-intercept at 2? Because I looked at the picture and I saw an x-intercept at 2. That's how I know. You know, that's there's always going to be that battle of like, why do we have to do it this way? And you know, and honestly, it's a tough explanation to give, and it's not one that really always lands. But you know, like I always have this idea that I'll show you a simple case. I'll show you a simple, all my students, all my classes, show you a simple example, and then leave it to you to say, okay, so when the time comes, anything that I see that's similar in structure to this, even if it's very complicated, I could still use this technique. All right. So we learn everything that we can about the physical world so that we can expand outward or extrapolate to the parts of the physical world that we can't perceive. Right. So right now we're studying every aspect that we can about two-dimensional math. And you spend years doing it. Really, I mean, everything builds up to, you know, up to and including calc 2, maybe some differential equations. But that's all the study of two-dimensional math. Maybe you touch on three-dimensional stuff here and there. Then you get into calc 3 and linear algebra, and that's when you start expanding into three-dimensional 3D space. All for the purpose of understanding spaces beyond 3D. Right? So, because once you recognize something is true in all dimensions, then you can apply your knowledge from 1 dimension, 2 dimensions, 3 dimensions, into 4 dimensions, 5 dimensions, and so on, and know that it's going to be a fact. All right. For a lot of folks, it's like, well, I'm never going to take those classes. That's possible. All right. But I always teach as if you are. All right. Because you never know. So anyway, I mean, some of you do know. Some of you are like, oh no, trust me, dude, I'm not taking those classes. But it doesn't mean that you can't ponder. You can't think about it and become fascinated or interested by it. Lord knows I have. Anyway, I honestly don't know why there's such a huge space here. I had no intention of writing anything there, so that's another typo. I also don't know why there's such a huge space here. I guess we'll call that another typo. So this should be That shouldn't be there. I don't need any of this space. I don't need any of this space. I guess I need some space for this problem, but that's neither here nor there. Okay. So example, find the derivative with respect to x of the function. Now we have an absolute value function. Now you could graph it to absolute x minus 2. Close it up, tack on a 2 at the end, zoom out, turn off the absolute, and you can see that the calculator, the Desmos calculator, can handle perfectly well derivatives of absolute value functions. Okay, so that's pretty nice. Okay, we're going to go through the process in a sec anyway, just because I want to make sure everybody's comfortable with it. But at its heart, an absolute value function is two linear functions put together. And we've kind of directly and indirectly addressed this. The derivative of a linear function is just that linear function's slope. There's no work to be done there, right? So you kind of rely on that sort of recognition. But what we want to be able to do is write this as a piecewise function so that we can look at each part independently. All right. So we have f of x is going to be equal to 2 pieces. All right. If you have the graph in front of you, there's no reason why you can't use it. I know that the slope is going to be plus or minus 2. All right. One part's positive, the other part's negative. I'm working on the downhill slant here. Oh wow, that's fun. Okay. That's not what I wanted to do. But now that I know that the Apple Pencil can do that, I don't know how I can benefit from it, but it's nice to know. All right, so I'm working on a downhill slant here. I have a y-intercept of 5. So my first piece is going to be negative 2x plus 5. Oh, I'm sorry, 6. I see a 5 right in front of me, and I just go after it like now. It's a 6. There it is. All right. So then, since I know the slope count is 2, I can work backwards here and see that we're looking at, for the other piece, it looks like it's going to go down to a negative 2, so 2x minus 2. If you're not sure, type it in. All right. If you're really not sure, but you know the slope, put in a placeholder variable like a, create a slider, and just slide your slider until you get equivalence, and you'll see it's latching onto a negative 2, and there you go. All right. So there's a bunch of different ways you can use Desmos to your advantage. Right. So now we just need a domain. So if now we have a solid point here, the function exists at that location. Like if I evaluate this function, f, so at the corner, right? So I'll just make a note here. There is a corner at x equals 2. All right. If I evaluate this function at x equals 2, I'm going to get a 2. All right. So f of a exists. All right. It's a question of whether my derivative exists at that location, but we'll get to that in a second. All right. But I have a solid point there. So I could say this first piece exists if x is less than or equal to 2. And this second piece exists if x is greater than or equal to 2. I can mix and match less than symbols with greater than symbols because we have a vergence of those two lines. So we're good to go. All right. Either way, I mean, if I wanted to make this one a less than with that one a greater than or equal, the only thing I wouldn't be able to do is have one be less than and the other be greater than. One of them has to have an equal in it. All right. What some people will do, and I, for the life of me, can't understand why, is they'll say less than, greater than, and then throw in a point here saying 2 if x is equal to 2. I mean, that's just, I don't like that. That's just making it unnecessarily complicated. if you want to make, when you make a piecewise function, you want to do it with the least number of pieces as possible, right? That's always the strategy. So then f prime of x, the derivative of a linear function is just the slope of that linear function. So -2 and 2. And we can verify that because if you look at these horizontal lines, the one on the left, in every instance, it has an f prime value, the y value that's dependent on x of -2. It's always -2. And this one always has a y value of +2, regardless of the x value, right? It says undefined here, but that's just the calculator being difficult, right? Because it is a defined value, right? Or at least one of them is, because it just because, you know, you wouldn't necessarily expect both of them to be, because then it would fail the vertical line test. But one of them should be defined, right? So it's kind of like when you assume one is defined, then it says, no, just kidding, I'm not defined, it's the other one. And then you go to the other one, it's like a seesaw back and forth. So the calculator gets confused and just says that they're both not defined at that location, right? So if you want to play it safe, you could say if x is less than 2, if x is greater than 2, but you could make one of them greater than or equal and the other less than or equal, or vice versa. The only thing that you could not say here is something like this. This would not be true, because if you did that and said that there was a solid point at this location and here, it would fail the vertical line test and not be a function anymore. All right. So that wouldn't play out. But this is the safest bet, but you have some wiggle room there. All right, as long as they're not both defined at that location. Right. So then
I have a
when I'm
question.
looking, yeah, sure.
How would you find the parameters in like in a normal problem? Like, how would you know that it's x is less than or equal to 2 for each piece?
It would actually be the same way. You would work off of these, but then you would ask yourself, all right, well, what would the coordinates be at this endpoint? You would say, all right, let me look at f prime of 2. I would get a -2, all right? And then you'd look at this one and say, what would I get at f prime of +2 for this piece? And it would say 2. And because there's a conflict, you would have to say, well, it can't be both, so you got to pick one. Right? So since there's a conflict, if you were to plot, you would be plotting at 2, a +2 and a -2, which could never happen in the function. So since there's a conflict, you can either look at it as, okay, they cancel each other out, right? It's irrelevant. So let's just say less than in both cases. Or you could say, all right, well, only one of them exists. All right, so you could say it's this one, the top one that's the closed circle, but the bottom one would then be an open circle. In which case you would say, oh, well, I guess it would be the top one. Yeah, that would be the greater than or equal. You could say it like that. Or you could go the other way around. And say less than or equal with a greater than, right? So it's really just going by points without saying, okay, let me put this in a graphing calculator and see what's going on. Right? But it's still a graphical approach. It's just you're not using technology. Right? So because we have that conflict there, that's actually going to set us up for the test. Because what this is saying is find the limit as x approaches 2 from the left of f prime of x, and show that that's not equal to the limit as x approaches 2 from the right of f prime of x. Whether the points existed or not at these locations is irrelevant, because remember, when you're finding a limit, you're finding what the y value would be getting closer and closer to, what the y value is approaching, what it's aiming for. It doesn't actually have to get there. All right. So as I come in from the left, I'd say, all right, what y value am I getting closer and closer to? As my x value gets closer and closer to positive 2, you'd say, well, the y value is never changing, so I guess -2, and you would be right. Then from the right, you'd say, all right, what's my y value approaching as my x value is getting closer and closer to 2 from the right-hand side? And you say, my y value is not changing, so I guess +2, and you'd be right. Because these are not equal, this justifies a corner. All right. So now, bearing in mind, they didn't ask us to do any of that part of it. All right. So they just said find the derivative. So we were done with this problem right here. But it wouldn't have been much of an example if I cut it off the download. There was more to it. All right. So the one example that I haven't talked about yet is the case of the cusp. But let me come back to that because I think I beat you over the head a little too much with these with the cube root functions. And the best example of a cusp actually involves a cube root function. And I don't have the heart to put you through that. So I'm going to show you the shortcut rules, and then we'll come back to the cusp example. So let me slip another page in here. It's more so to remind myself. I'll say cusp example. And so it'd be f of x. The classic one is x to the 2/3. All right, but we'll come to that in a second. I just wanted to get into some shortcut rules because these make life a whole lot easier. All right, doesn't really get at the theory of why you're doing what you're doing. So, you know, like, do I regret spending so much time on this other stuff, you know, with the limits and all that? Well, only in the sense that it's time that in your life that you'll never get back. But I don't regret it in the sense that there's valuable information there and it will help you in the long run. The problem is the long run is a long way away. So you won't feel it quite yet, but when the time comes, if you take the time to make sure that you understand all this, then there will be a substantial payoff for you. All right. So I keep saying that, and I really probably should stop just because at this point you either believe me or you don't, and it won't be for some time that you really get a sense of whether I was right. So you have a few rules. One of them is a constant rule. The derivative of a constant is equal to 0. That's wonderful. Okay. It's also, I'd like to say, a fair amount of common sense, but only if you know what a derivative is. So if I tell you you have a function f of x is equal to 5, that's a constant function. Constant means unchanging. All right. A derivative is a slope of a line tangent to the curve at any point along the curve. Sounds fancy. All right. But at its heart, slope of a line. Okay, well, slope, rate of change. Rate of change of something that's constant. Right? Constant is unchanging, no change. So the rate of change that something is constant, that of something that is constant better be 0. All right. The y value never changes, no matter what the x value is. The slope is 0 for any constant function. Constant functions are always horizontal lines. All right. So no matter where I put it, f of x equals 0.7 or -4.3 or -9.2, it's always going to be a horizontal line. And the slope or the derivative will always be equal to 0. All right. So the power rule. a fun looking rule. It's really just telling you to take the exponent, multiply. I mean, it doesn't seem obvious, but assuming your original function has a coefficient of 1, then what this is saying is the derivative of the function now we're only working with functions at this point, so I'm not incorrect in saying that it's the derivative of a function, but it could be any equation really, right? Or any expression. But the derivative of this particular function is this, all right? So this notation is saying the derivative of this expression, this function, will give this as a result, all right? But the structure of it says, if I take whatever this power is, this n, and multiply it by this coefficient, and then reduce that original power by 1, I'll get my derivative, right? It's actually very straightforward. But the notation tells an important story, because if I say d dx parentheses f of x, I'm really saying the same thing that I was saying before when I would say f prime of x. All right. So if I have a function of x and I slap a d dx in front of it, its notation saying d dx of f of x, then I'm really saying f prime of x. Now that d dx, yeah, it means the derivative, but it also means with respect to x, all right, which has been a source of confusion for decades, centuries for students, because it's like with respect to, what the hell does that mean? It just means that the relevant variable within the function is x. Well, that should actually kind of make sense, because when I say f of x, I'm saying here's a function and the relevant variable within that function is x. So all this is saying is I am going to take a derivative and the relevant variable within the derivative is x, all right? There will be other instances where we'll have multiple variables when we get down the line, and one of them will be the variable of interest and the other one will be just another variable, and I'll show you how to handle that, right? But also, we know that in many instances, in most instances, we think of y as being equal to f of x. So that makes y and f of x interchangeable. So instead of saying d dx of f of x, I could say d dx of y. All right. A shorthand way of writing that would be, if I were to combine these two things together, the d and the y, I would say dy dx. All right, dy over dx, which is saying the derivative of y with respect to x. All right, all of which is equivalent to f prime of x. All right, so all of this notation, and actually everything I've been saying for the last week or so, is boiling down to, regardless of the instructions, the way it sounds, whatever the question's asking, if it doesn't say limit, it's probably telling you to take a derivative. All right. So whether it's a slope of the tangent line, or find the instantaneous rate of change, or the equation of the tangent line, or the derivative, or differentiate, it all means the same thing. All right. So when you look at this first example, f prime of x is what I'm going for. We have the understood 1 in front of the x to the 5th. All I'm doing is I'm taking that 5, multiplying it by the 1. 5 times 1 is 5. Reduce the exponent by 1. So 5 minus 1 results in 5x to the 4th. Okay. F prime of x, understood 1. 10 times 1 is 10. X to the 9th power, reduce the exponent by 1. All right, same general idea. For the next one, it says f of x is equal to 1 over x squared. It doesn't fit the model quite as well as the other ones. However, if I rewrite this as f of x is equal to x to the negative second, now it fits the model. So you could have negative exponents. So understood coefficient of 1, multiply the power by that coefficient. So f prime of x, negative 2x, reduce your exponent by 1. So negative 2x to the negative third. And then you get to the one that maybe caught your attention immediately when you turn to this page. You see the cube root of x. We've already done this with the limit definition. That was that one that raised holy hell in the beginning of class. I can rewrite that as f of x is equal to x to the 1/3, understood coefficient of 1, multiply the power by the coefficient, f prime of x will be equal to 1/3 x to the 1/3 minus 1, which is 1/3 x to the negative 2/3. Now, if you simplify that by bringing the 2/3 down to the bottom of the fraction and negating it, you would say 1 over 3 x to the 2/3, which is what we got before and in a fraction of the time. So yeah, do I feel bad about that? Yes and no. You needed to know the algebra. It will help you in the long run. But, you know, if I looked at the clock, it's probably like half an hour of work, at least maybe 45 minutes of work, 40 minutes of work to do one problem, as opposed to the 45 seconds it took to do this one. You know, so that one part I do feel a little bad about, but really, unfortunately, not much else. Right? Constant multiple rule. That's a fun one, because what that's telling you is you could actually use this power rule the way I just described it, even if the coefficient is something other than 1. But it basically tells us that we can tackle these problems in a couple of different ways. The constant multiple rule tells you that if you have a multiplier that is a constant, right? So in the case of the x cubed here, you see a 4 in front. Right? What this tells us is that we can hang on to the coefficient, take the derivative of the parent function, and then bring the coefficient back in later on. So I'm going to show you 2 ways to handle this one. So we could look at this as f, oh, that's not a marker, f of x is equal to 4 times x cubed. And then we could look at this as f of x is equal to 4, just a 4x cubed. And you're like, okay, that's exactly the same thing. What are you going with here? Right? So if we look at the first approach, this constant multiple rule, it'll seem nonsensical right now, but when we get to more complicated issues, there we got issues. Right? So when we get to more complicated problems, it'll become more obvious why this is important. So I'm going to go with my understood coefficient of 1 in front of the x cubed, multiply power by that coefficient, reduce the power by 1. So f prime of x would be equal to 4 times 3x to the second, which would in turn become 12x to the second. Or multiply the power by the coefficient 4, f prime of x would be equal to 12x to the second all in one shot. And you would look at it and say, well, of course I would do it this way. But when we get to some of the beefier functions that we're going to work on, you'll see that there are plenty of instances where you would say, all right, well, that coefficient is going to make things way more complicated than it needs to be. Let me just hang on to that coefficient, leave it out for a little bit, take the derivative of the main expression, and then bring that coefficient back in after the fact. All right? But all these remaining problems are some variation of the power rule. So I'll put stars on these. Yeah, I guess I don't need to put stars on every one of them, but I will. And the last thing that we'll do is this cusp example real quick, because now that we know the power rule, it's gonna be a whole lot easier. Okay, we don't have to use a limit definition. So what I'm gonna do is go with my understood coefficient of 1. I'm gonna multiply my power by my coefficient. And we're gonna say f prime of x is equal to 2/3 x to the 2/3 minus 1. You don't have to show that step. I'm just doing it because I know a lot of people are new to this. You know, some people already knew the power rule going into the course and they're just waiting for me to unleash it. But I know there's a lot of rookies here, so I want to make sure I give something for everybody. So 2/3 x to the negative 1/3. All right, because if you want to do it in your head, you know, you go to a calculator if you want, but if you want to do it in your head, then whatever the denominator is for the fractional exponent, you're just subtracting that denominator over itself. So that 1 is really the same as 3/3. So you just bang it out that way, 2 minus 3/3. Right? You know, if you're not used to thinking about numbers that way, it might be an adjustment, but it should get easier and easier. Right? It's gonna make this F look a little bit more tidy. All right, so for a cusp, we want to first make sure the function exists at the point. And so we're going to say we are going to analyze f of x when x is equal to 0. All right, so that's the relevant location for the cusp. Tuck that in there. All right, so we need to first make sure the function exists at 0. So 0 to the 2/3 is equal to 0, so that's good. All right, if you evaluate your derivative function at 0, now another way of writing 2/3 x to the negative 1/3 is the same as saying 2/3x to the positive 1/3. So you don't really have to do much number crunching before you realize that this is undefined, which is typical. I'll just write it out. All right, so we're good to go there. So then what we would want to do is find the limit as x approaches our point of interest, which is 0 from the left, of my derivative function f of x, f prime of x, sorry. And the limit as x approaches 0 from the right of my derivative function, again, f prime of x, and show that they go to opposite infinities. All right, and you could use the calculator to support your work, because otherwise it's number crunching. I mean, you really have to make a table of values and simplify. I mean, most people are not overly interested in doing that, especially since you're probably using a calculator to get said table of values. So here's my x to the 2/3. Definitely looks like a cusp at 0. You tap, you see that it exists at 0, so we're good there. Then I just pop in my f prime of x. It's showing that I should have a blue graph. I don't see a blue graph, which means that I should probably be zooming out. I am zooming out, and there we go. I'll just hit the negative 10 to 10 and then go back in. I'm going to turn off my original function because it's distracting me. But if I look at my derivative graph going from the left, as I get closer and closer to 0, it does appear that I'm going down forever. As I'm coming in from the right, it does appear that I'm going up forever. All right. So, and again, if you're not sure, you just zoom out a lot, zoom back in until you see what's going on. I'm looking for one curve here. If I see 2 curves, then that means they're both going to the same kind of infinity, and that would be a problem. No matter how much I zoom in, I'm only seeing one curve. All right. When I go down forever, and then bring it back in, I'm only going to see one curve. All right. That means one part is going down, the other part's going up. From the left, we're hitting negative infinity, if we could ever get there. From the right, we're going to positive infinity. These are opposite infinities. Therefore, we have justified the cusp. All right. So yeah, a lot going on with that, but the one thing that didn't really take too much time was actually finding the derivative. It would have if we were stuck with the limit definition, but you know, now we're graduating to some shortcut rules that are making life a lot easier. All right, so I think that's a good place to end it for tonight. A lot of stuff to think about over the weekend. So so definitely take the time, study, and you have a tech assignment that you could be working on, all that good stuff. So if you have any questions, stick around. If you came in late, check with me before you go. Otherwise, enjoy the rest of the week, and I'll see you on Tuesday.
All right.